All right, well, hi everyone. I hope you're having a great day. I'm happy to welcome Julie today. And she will be talking to you guys about how the CodeDay matching algorithm works and kind of the iterations and steps that it took to make that happen. So, Julie, if you'd like to introduce yourself a little bit more, and then we can get started.
Yeah, fantastic. So I'm Julie Cover. I used to be a software engineering intern at CodeDay. More recently, I'm currently working for Keysight Technologies. We're doing network test equipment. I'm a junior computer science engineering major at UCLA, and I designed and implemented the backend for the student mentor matching that we used for CodeDay Labs. Um, yeah, so this talk is basically on how we matched you to your Code Labs team. So really quick, there's going to be 3 or 4 parts to this presentation. Going to start with an overview of the problems that I needed to solve and some other similar problems, as well as some basics of algorithm design and algorithm design principles. And then we're going to go over an in-depth explanation of what I did to solve the problem as defined, with a side of algorithm design tips and suggestions that you can hopefully learn from. And finally, we're going to talk about lessons learned from taking another crack at this more recently. So let's quickly get a little mini crash course in algorithm design. The first most important part of any algorithm design problem is to consider the problem that you're trying to solve. So specific details are very important. It's definitely all too easy to kind of solve the wrong problem or something very similar, but not quite what you needed to. Consider like an algorithm to decide if someone is famous. It's very important to define what that means. You could consider it to be solving for someone who is known by the majority of people, or you could consider it a more complicated and in-depth definition, like this person is known by everyone else, but this person does not know any of those people themselves. Both of which are possibly valid definitions for that problem, but they're very different in how they'd be solved and what the result would be. It's very important when you're working on anything that's algorithmic to work with your team or whoever you're basically working with to ensure that you're solving the correct problem for what needs to be solved. Next important thing to touch on is optimality of algorithms. So in algorithm design, we have like optimal algorithms. Basically, that means that you can prove with like a robust logical proof that this provides the optimal solution to a problem. This means if you've ever used induction or done like a mathematical proofs class, it's very similar to that. It's great when you can find this, since it means that you have the perfect solution and you can easily prove this to others. But sometimes there's more to an optimal solution than meets the eye. So in some cases, you have an optimal solution that actually has a lot of caveats or takes a long time to run. We'll see 2 of those in a minute. And in computer science education, we focus a lot on only caring about optimal and solving, like finding optimal solutions and only solving for those. And in my opinion, while it's important, it's not really the end all be all. There's a lot to be had in algorithms that can't be solved optimally, but are still can be solved to an effective degree. Um, but yeah. The next important thing is runtime and big O notation. This is like the last of the quick little details we need to go through in our algorithms crash course. So different types of algorithms can take wildly different times to run. Consider an algorithm where you need to choose an arbitrary number between 1 and a number of someone's choosing. Because it's an arbitrary number, you could just choose the number 1 every time. That would be an algorithm that runs in constant time for this. You can see how it always runs, at the same time, no matter how big of an input you give it. But if you need to do an algorithm that has a nested for loop, that, as you could see, would run in polynomial time. So it would be, squared time, basically, because for every item, you need to process every other item. So different types of algorithms, like I said, can vary wildly in this runtime property. And we estimate it through something called big O notation, which tells you roughly in general how an algorithm will perform on a very large data set. So it's written like this: O parentheses and some numbers, with usually an X or an N representing the number of inputs. So we have constant, logarithmic, which is going to be slower than constant, but faster than linear. Then we have linear, and then we have polynomial. So Some algorithms, though, are actually even slower to run. These are called hard problems, or NP hard problems, called because they're non-polynomial and hard. You may have heard of the traveling salesman problem, which is a well-known exponential time problem. But there's actually multiple different kinds of NP hard problems of different hardnesses. There's exponential, factorial, and I forget the name for x to the x, but I believe it's hyperexponential. But these are deceptively slow. Consider an algorithm with a factorial runtime. If you want to run it on one item, it'll run an O of 1. But if you want to run it on 10 items, it'll run 3 million times slower. With 15 items, it'll be 1 trillion times slower. And I think I checked for 300 items, it was something like 2 times 10 to the 90 times slower, which is just an absolutely unbelievable amount slower. So clearly, algorithms at this speed are just totally impractical to run in the real world. However, oftentimes, like Amazon, they have to solve the traveling salesman problem on some degree to be able to find a reasonably optimal way to deliver packages. So what we can do is we can actually find an approximation of the solution using a different approach, and we'll talk about that more in a minute. But I believe this is something that's really important and not super touched on by modern algorithm education. So I'm going to be taking Q&A at each of a couple breaking points in the presentation. This is one of them. I have a Q&A. Algorithms after. Fantastic. Some of these questions are funny. Anyways, so let's start by looking at the background on what the specific matching algorithm and such things for CodeDay Labs entailed, and some other problems like it. So there were two main phases to the CodeDay Labs matching. There was the priorities and recommendations phase, and then the placement phase. So these were actually handled very differently. Priorities and recommendations was done using Elasticsearch, which is a tool used to create search engines and recommendation things. And we used it to recommend the best projects for you based on your application. Then the second phase was the placement phase, which based on everyone's priorities, we needed to assign everyone to an actual final project that would be their project for the year in a way that is fair to everyone. So here we overlapped with some of the more traditional matching algorithms that we talked about earlier. And I spent some time researching those. We'll talk about it in a minute. So the most common matching algorithm is the Gale-Shapley algorithm, also sometimes called the stable marriage problem. Essentially, it works when you have two groups and both have an ordered preference of one group into the other for all members of the other group. This doesn't work in our case because only one group has priorities and it's not a complete list. Furthermore, stable marriage is only favorable to a single group, and while it means that there won't be any matches that make both parties happier if you switch them, it's actually very bad at finding a middle ground. And it has a runtime of O log n, n log n. But another common problem that you'll find is the stable roommates problem, which does not require preferences on all members, but only has one group. And again, that's a no-go for our problem. It turns out there actually is a name for the problem that we're trying to solve, and it has been solved before. It's called hash-strong stability. It handles ties and incomplete lists, which is actually perfect for what we want. However, someone who's much smarter than me, some PhD student at the University of Glasgow, has actually shown this problem to be NP hard. If you remember, that means that there is not a provably optimal solution that can be found in any reasonable runtime whatsoever. So we can't actually use this solution. However, we still shouldn't give up because we can actually get to a really good approximation of this solution in a very reasonable runtime, which we'll see later on. So now we're going to go over the solution that we actually used for the whole matching process, with a side of some algorithm design tips on what I learned as I was going through this. So the phase 0 of any project like this is data collection. In this case, it matters a lot what kind of data you're starting with to basically do the matching. This was the schema we used for the data from last year. It's possible it's slightly different this year, but I definitely think we stay with something similar. Why this matters so much is that if you don't have reasonable data to do matching and recommendation on, there's just not much you can actually do. If you only have people's names, you can't do much of recommendation with that. So we focused on collecting lots of data from mentors and students in the interview and application process that we recorded and fed this through our algorithms in order to make a good educated decision on, on who might be a good fit for the program and the good projects for them. So important note is that none of this algorithm stuff was involved in accepting or denying applications to the program. That was 100% manual human review, since there's no way we could build a good enough automated system to review applications. We thought it was really important that we have a human touch in the application process. So for matching, we use something called Elastic. It is a database product by, I forget who, probably, I don't remember. But anyways, it's a database product, very powerful, but really complicated and very frustrating. So my biggest gripe with Elastic is that the docs feel like they're from another era where programming books or classes were the only way to learn anything. I'm sure many of you are self-taught sorts of computer science students, as many of us are today, and this is a little bit frustrating coming from that sort of experience with the web and things like that. It lacked a good starting explanation for beginners and really lacked examples altogether. If you've done any Android development, the Google APIs and Android documentation are full of examples and things like that. This is basically the opposite of that, which is unfortunate. Additionally, the Python tooling is a little hit or miss. There's many different ways to do it, none of which are explained well in like an overall thing. Python has, or there's like some libraries that have more tooling, some of which are better. No matter what, though, if you're doing anything complicated, you're not really going to be writing Python. You're going to be writing some of these script queries in the Elastic Query language, which is basically Java with extra steps and a complicated standard library, which was an absolute nightmare to work with. But you're very limited in a bunch of ways. You could definitely figure it out. Just remember, it'll be an adventure to figure out, though, at the very least. Finally, the portability of Elastic projects is actually kind of fantastic. Because you write all of it in that weird other Elastic query language, you can actually port it to like anything that you want. So later we had to port the whole logic to TypeScript so it could run in our Node.js backend. Here it was super beneficial that most of the logic was in those other DSLs and things like that, the fancy Elasticsearch language. So it could be translated very easily. As much as I've been a little bit complaining, Elastic is incredibly powerful. There's not really another good way to do search and matching. I've tried it in Postgres, which is an SQL database, and it's just a nightmare. It's trying to solve a very difficult problem, but when everything works, it just like kind of works amazingly well. And we definitely benefited from the weirdness of the APIs from when we did the translation. The complexity like this is kind of inevitable in something this general and powerful, but bad documentation and language APIs are not inevitable, and they definitely could have done something about that, and they should. At the end of the day, I really feel like if you're doing this, my recommendation is buy one of those books. They'll serve you pretty well. Next, you need to take your new matching tool you just built and hook it into other tools if you want to actually do anything with it. To do that, you need an API. So APIs are part of the whole web ecosystem, and they're much better documented than Elastic and those kinds of things. In my opinion, GraphQL is just straight up the best way to do APIs today. It's kind of an alternative to the more common REST API you might have heard of. It enables you to write one big schema instead of a bunch of endpoints, and then you can query that whole thing for all of the data you could want for anything you need to do on the front end. It's really easy to integrate into front-end frameworks. The back end is no harder to write than a REST API. Strongly recommended. And it has this is kind of a tangent, but it has this tool called Type GraphQL Prisma that is just, it just writes your entire backend for you based on your database configuration. My favorite way to do anything like this. So now that we've learned how the recommendation algorithm worked, let's talk about normal algorithm design. Here are some basic tips you can use as a starting point for your thing and a review of my process. really important to start with a lot of planning. It doesn't matter if your first plan is very good. You just need to come up with something that you can think of to solve the problem and go start from there. It's really important to do both brainstorming and a lot of online research. You'd be surprised, so many problems have been solved already. Doing a day or two of research to find a solution in some PhD student's research paper will save you so much time later on, if it's possible. It'll also be able to tell you if your problem is hard. If it is NP hard, you basically just need to get creative. You can either go back to the drawing board and see if you can adjust the problem a little bit, change the problem scope. Like in this case, we could have tried to make the students rank all the projects, which would have been pretty slow to make all the students rank all of them, and it would have been unsustainable in this case. But if we only had like 10 projects, we could have made people rank all of them, and then we could have used Gale-Shapley in that particular case, or one of the other algorithms mentioned earlier. If you can't do something like that, though, your best bet for a hard problem is just to get creative and think of some other way to approach the problem, which I'll demonstrate in a minute. That's really the best way to solve things like that. If it's not NP hard, you can usually find someone else's solution to the problem with enough research. You can try and implement that yourself in your own language, whatever you're doing. That's honestly a pretty good bet. These PhD students, they tend to be pretty damn smart. So it's a good choice to go try and do something like that if you can, to use just because it's a very robust, optimal solution that you can often find that'll save you a lot of work and get the project done faster. If you're coming up with your own approach, and even if you're not, it's a good idea to go through and revise and break your problem, your solution iteratively. You want to spend a while thinking through edge cases, trying to come up with ways that your algorithm totally fails, and trying to solve any issues you can find before you start writing any code. You need to do this a bunch of times because it's never really a good idea to get started right away with something like this. It's much easier to plan and rewrite it and come back rather than, or plan before you have to rewrite it and just keep rethinking it, rather than get all the way through an implementation, realize at the end that your whole thing is bugged and that you don't have any plans. Yeah. In all seriousness, run your plan by a few people to see if they can find a problem with it, to see if there's anything there. Next thing is you need to start implementing it. This is a bit more wishy-washy. This is just programming. Once you have a solid plan, it shouldn't be too hard to write it out. It's important to keep in mind, though, if you're using, I don't know, pretty much whatever language you're using, avoid what am I looking for? Avoid memory issues and make sure you write it in a way that is reasonably efficient. Again, algorithm choice mostly dictates speed, but you can still write a program 10 times slower than possible, even without using a bad algorithm. So just when you're implementing it, try and keep in mind speed, but don't over-optimize. Don't really optimize too much before it's needed. Inevitably, some unforeseen thing will have made it through your revising and breaking cycle, and definitely happened to me, definitely happened to you too. In this case, you want to take a step back and really analyze your issue to make sure whatever patch you come up with is as generally applicable as possible. In my problem, I realized I was losing students. Like at the end, they just kind of weren't anywhere. And the problem that I found was that they didn't actually get placed into any project by the end because somebody else had a higher priority for all of their choices, basically, and so they never got their choice. So it turned out this was basically a flaw in how I was originally choosing to allocate the students, and I needed to change that part of the algorithm a good little bit to make sure that people will be placed more in these cases. Finally, you also need metrics so you can tune your algorithm over time. It's really important so you can make small tweaks and just see how the results come out if you're trying to solve a hard problem in a bit of a janky way like I've described. In this case, I was able to figure out that with some tweaking, I got the overall average choice down to about 1.52 on the whole data set, which meant that most people got their first choice, which I was pretty happy with overall. Finally, you may realize that there's more improvements to be had in pretty different ways. So in my case, I realized that the best way to deal with a tie-breaking problem that was the crux of the problem that made it NP hard was not to actually solve it the way that the paper suggested. Instead, you could just, if there's a tie, randomly choose who wins and run the algorithm 50 times, and then take the best result. And it turns out that works really well. That totally stopped any students from being lost and lowered the target number, because and at the same time, we were still running in basically linear time because we had to multiply it by 50. But again, compare that to the, what was it, for 300 students, it was 2 times 10 to the 90. It's so much faster just to run it 50 more times than it is to try and solve like a factorial complexity problem in this case. So that's what I was talking about earlier about creativity when you're solving NP hard problems. There's many ways to skirt around the defined complexity of this problem that you might see, and just keep in mind thinking about things like that. In case you're curious, here's what my final placement algorithm plan looked like. However, this is totally illegible on a slide and also basically entirely unimportant. What's important here are the general ideas present in that are make it into what I think is a pretty good choice for an algorithm like this. First off, there's multiple steps. So with code, you're not really beholden to anything. So you can basically make as many passes as you want. Most optimal algorithms don't have an iterative approach like this. They often take a single small step and repeat it for all items. But when you're solving hard problems like this and you don't really want to solve it, sometimes that doesn't really work. So you need to take other things you need to like create some heuristics and just solve smaller parts of the problem in a way that gets you as close to a good result as you can get. Second, here with this problem, the descriptions are clear in their intention. The best way to write this is even more than this, which wouldn't really fit on a slide, but in terms of bullets with just like small steps, like for every item, do these 3 things, that kind of thing. That's both the easiest to think about and analyze and the easiest to translate into code. So keep that in mind for when you're writing descriptions of your algorithm. Writing it down even is super helpful just to find problems with it, but yeah. And then third, make sure you decide at this step where you want your metrics and checks to make sure that everything's working properly. They will be incredibly helpful in optimizing it later. So strongly recommend this part. Now, manual cleanup is kind of a last step sometimes. Sometimes it's the fastest way to finish up, since you can have diminishing returns as you have to finalize your development process. Sometimes it's not possible, though, if it needs to be integrated into an API. So just keep in mind if this is an option for you. It definitely can help sometimes. Recently, I took a whole other crack at this algorithm to make it fit into a new set of constraints, and I learned a lot more the second time. So first, working around NP hard problems. CS is absolutely full of these. Sometimes you'll see people just totally ignore them because the optimal solution isn't practical. Like they won't even try to solve it. Particularly, you'll see that with the halting problem. No one ever really tries to solve that, it seems like, even though you could totally get close. In my opinion, this is like a totally wasteful approach. Like I said, you can get close to a solution in a much faster time, and you'll end up with something most of the time more than good enough, infinitely better than nothing. In this case, like I said, with the randomness thing, I was able to take what's an NP complete problem and solve it in no event, which definitely helps with this dramatically. Secondly, sometimes project scopes change, as we saw here when I had to rewrite the whole thing from Python into TypeScript. Make sure you're flexible with that. Lots of things happen outside the scope of just your project by itself, and you just need to be flexible with the changes that are needed from everyone else in your team. Finally, I used to have this conception that a fast language like Rust or C++ was absolutely critical for algorithms like this. However, I now think that's a little bit silly. Algorithm runtime is by far and away the most important part in anything like this, and changing the language you use will really only ever result in a small linear time improvement. At the end of the day, what's most important is if your algorithm takes 15 seconds or 15 years, not whether it takes 15 seconds or 30 seconds. So just keep in mind the algorithm choice by far and away the most important part. If you really have to, you can try and choose a fast language, but oftentimes it's better to choose a language that you can write less buggy code in and write it more efficiently and will integrate with everything else your team is doing. Finally, a quick speed round recap of the technologies used in this project, just so if you want to make a decision based on that. Cognito Forms allows you to make really great web forms that can be embedded and themed to look like your brand. So that's a good choice. Elastic is really complex, does the job well, but the docs are frustrating. And because it's so complicated, it's really hard to figure out sometimes. There's probably some other options in the weighted search result sphere, but Elastic is definitely king, and it's just kind of the toolbox that people use if you're not like gonna do it all from scratch like Google. So definitely recommend giving it a try if you're doing something like this. Python is amazing for doing this kind of algorithm design and iteration because of the libraries that it has and just the tooling that it comes with. And Jupyter Notebooks alone are a huge selling point. GraphQL is basically the best way to write APIs for most things today that involve lots of data. TypeScript is just the best. It unlocks and tames the absolute disaster that is JavaScript. I use it in literally every project possible. So definitely strongly recommended. With that, thank you for coming to my talk. I hope you learned something that you can take away from this. If you have any questions, feel free to reach out to me somewhere over here. And my slides will be on GitHub there. Also, Code Day is pretty great. We're going to be putting on, I think, in-person Code Day starting again soon in many cities around the world. So all of you here are definitely going to CodeDay Labs right now, but I strongly recommend going to an in-person Code Day if there's one in your city as well. It's been some of my favorite experiences. Anyway, that's all I have. Thank you so much.
Thank you so much, Julie, for the wonderful talk and for giving all that information on algorithms and your process through this complicated problem. I really appreciate it. If anyone has any questions, you can definitely ask them in the Q&A. We'll wait a bit for those to come through, if there are any.
Yeah.
Okay, I think, yeah, I think that
Awesome.
should be all. Thank you so much again, Julie, for
Yeah.
coming today. Thank you.
Thank
It
you
was
for having
great.
me. Awesome.
Of course, my pleasure. All right, have a great day, everyone.
Yeah.
Bye.
Bye.